This is the screencast for section 2.4, example 4. We're going to explore the slope of a curve, the slope and tangent. I don't know, explore is such a weird word in math, but we're going to find the slope of the curve at x equals a. So what if you don't have a specific number, you just want x to equal anything you want it to equal at the end? Why do this for every number you want to find the slope for? Why not just come up with an equation at the end where you can plug in any specific x value? So that's what we're going to do. So we're going to use a comma f of a plus h comma f of a plus h, and we're using the equation 1 over x. So I use my difference quotient and the limit as h approaches 0, find a common denominator here. Simplify the numerator, multiply by the reciprocal of the denominator, simplify again. Now I finally have a situation where I can plug in 0 for h without getting 0 over 0. And I get negative 1 over a squared, which is awesome because if I want to know the slope at 2, I plug in 2. It would be negative 1/4. If I want to know the slope at 1, I plug in 1, negative 1. If I want to know, well, you get it. Okay, so then part B is another advantage. Where does the slope equal negative 1/4? So all I have to do is set negative 1/4 equal to the equation I found representing the slope, and I get that a is either positive or negative 2. So to answer the question, the slope equals negative 1/4 at the two specific x values, positive and negative 2. So what I did was I found out those coordinates on 1 over x, threw together a couple of equations of the tangent lines, and I graphed to make sure that there were two places where it looked like a tangent line would have a slope of negative 1/4, and these do. Down 1, right 4, down 1, right 4. These tangent lines intersect the curve at both 2, 1/2 and negative 2, negative 1/2. The now try problem number 19 says find the slope of the curve at x equals a. So same strategy as the example, and then describe what happens to the tangent line at x equals a as a changes. Alright, so let's one problem at a time here. Part A, I took, let's see, my 2 points, which are a comma f of a and a plus h comma f of a plus h. Now I used x instead, which is perfectly fine. So I went through and I used an x value to represent the unknown x value that I'm trying to find the slope at. I did my difference quotient, multiplied out, simplified, factored out an h, simplified again, plugged in 0 for h, and I get a formula 2x. Now this formula is what I can use to find the slope of the tangent to x squared plus 2 at any x value I want. So that's what I'm doing here. So to find the slope at a bunch of different specific x values, or the slope at these a values, I plugged them in. 2 times, what about when x equals negative 5, the slope is negative 10. When x equals negative 1, the slope is negative 2. When x equals 0, the slope is 0. When x equals 2, the slope is 4, which we already knew that one from a previous example. When the slope equals 3, it's 6, and then I'm like, oh, what happens at 100? Well, I plugged in 100, and the slope is 200. So I can make a general conclusion that the slope of the tangents to f of x are increasing as x increases. I know that doesn't sound like a huge leap of a mathematical conclusion, but it's true. As my x values increase, my slope increases. The rates are changing at a slope of 2. That is your mathematical leap. Y equals 2x is the formula for slope, so the formula for slope has a slope. Dun dun dun.